Hi, I am Dr. Sigarkanti. In this video, I will prove Leibniz theorem for the nth derivative of the product of the two functions. The statement of the Leibniz theorem is like this. If y equal to u into v, where u and v are functions of x having nth order derivatives, then nth derivative of this product is given by nc0, that is equal to 1, unv plus un means this is the nth derivative of u into v plus nc1 binomial coefficient nc1 un minus 1 n minus 1th derivative of u into first derivative of v plus nc2 un minus 2 v2, that is n minus second derivative of u and second derivative of v plus nc3 un minus 3 v3 n minus third derivative of u and third derivative of v plus last term ncn, this is equal to 1 into first derivative of u nth derivative of v, or if I interchange u and v, I can write yn like this also. nc0 uvn plus nc1 u1 vn minus 1 plus nc2 u2 vn minus 2 plus nc3 u3 vn minus 3 plus ncn un v. Okay, like this also we can write. To prove this theorem, I will prove this result by mathematical induction. What is mathematical induction? Mathematical induction is a process of proving the theorems. First, we verify the result for n equal to say 1, and next step is we assume that the result is true for n equal to m, and the last step is we prove the result is true for n equal to m plus 1. Okay, this is our mathematical induction method. Okay, here if I take n equal to 1, what is the left hand side? y1. Okay, y1, y equal to uv, y1 means the first derivative. Okay, first derivative. That is differentiating this with respect to x, I will get the first derivative, that is u into first function into derivative of the second plus second function into derivative of the first. So this is our left hand side. What is the right hand side? The right hand side is nc0. 1c0 is 1 u1v plus 1c1, that is also equal to 1 u0. u0 means differentiation of u 0 times, that is u as it is, into v1. Okay, so I am getting only two terms on the right hand side. I am getting here u1v plus uv1. Here also I am getting u1v plus uv1. Here also I am getting u1v plus uv1. So that means left hand side is equal to right hand side. That is the result is true for n equal to 1. Next step, I will assume that the result is true for n equal to m. That is replace n by m here. I am getting ym equal to mc0 umv plus mc1 um minus 1 v1 plus mc2 um minus 2 v2 plus and so on mcm uvm. This we are assuming. I have to prove that the result is true for n equal to m plus 1 also. So that means I will differentiate this with respect to x once. Differentiating this equation with respect to x once, left hand side ym is there. Differentiating, I am getting ym plus 1, that is m plus 1th derivative. On the right hand side, if you come here, mc0 is a constant quantity. Here, this is the product of two functions. I have to use the product rule. First function um, derivative of second is v1 plus second function is v, derivative of um is um plus 1. Okay, so this is the derivative plus. Coming to the second term, mc1 is a constant quantity as it is. Again here applying the product rule. First function is um minus 1, derivative of v1 is v2 plus second function v1 as it is, derivative of um minus 1 is uvm. Okay, that just I have to add plus 1 to this suffix plus. mc2 is a constant quantity. First function is um minus 2 into derivative of v2 is v3 plus. Second function is v2. Derivative of this, add 1 to the suffix here. Um minus 2 plus 1 is minus 1 plus sign, so on. The last term is MCM Vm plus 1 plus second function Vm as it is, derivative of u is u1. So that is, here I will write the group the terms here. Plus 1 terms. First I will write plus 1 terms. Only one term is there. This is the only term plus 1. Okay. MC0 plus 1 V plus v1. So here one v1. Here also we have v1. I will write this as MC1 plus MC0. Taking this v1 common factor, I am getting MC1 plus MC0 plus. Next I will write minus 1 V2 terms. Minus 1 V2 is here. Minus 1 V2 is here. Taking this minus 1 V2 common factor, I will get MC2 plus MC1. Okay. Plus, and next finally I will write this last term here. MCM Vm plus 1. Okay. Now, we have MC0 is same as M plus 1 C0. If this is 0, whatever may be this. Okay. And they are all equal to 1. MCM can be written as, replacing M by M plus 1 here, MCM can be written M plus 1 C M plus 1. And one more formula is there. MCR plus MCR minus 1 can be written as M plus 1 CR. Okay. MCR plus MCR minus 1. So this suffix is 1 less than this suffix. Then can be written as M plus 1 CR. Using these formulas, I will write this as MC0 can be written as M plus 1 C0 M plus 1 V plus. Here, applying this formula MCR plus MCR minus 1. So R equal to 1 here. This is our R minus 1. This can be written as M plus 1 C1. Okay. M plus 1 C1 I will write as M plus 1 minus 1 into V1 plus the next terms, and the last term is MCM can be written as M plus 1 CM plus 1 VM plus 1. See, this looks like, so in place of M plus 1, if I assume that it is N, how this looks is Yn equal to NC0 UNV plus NC1 UN minus 1 V1, okay, plus NCN UVN, okay, NCN UVN. That is, in place of N I have M plus 1. Let's make this a suffix. One. Okay. So that is the result is true for N equal to M plus 1. Then by mathematical induction we say that the result is true for all positive integral values of N. Now for problems, what I do here is I will use this one, second one. See how I will use is y equal to u into v is the function here. Okay, given function. To find the nth derivative, first I will write NC0. This is nothing but 1. I will write u and I will write the nth derivative of v. That is, choosing the functions u and v, we must know the nth derivative of one function. Okay, uvn, this function. And the derivative of this is increasing, derivative of this is decreasing. In the next term, NC1, see, I am differentiating u1 and this is nothing but 1 less derivative of this one. Plus next write NC2. Differentiate u1, I am getting u2 and 1 less derivative vn minus 2. So that is here. What we need to do here is, suppose the first function v is algebraic function, take that algebraic function as u and the other function as v. Because if I take the algebraic function as u, then after some time, after some turn, that becomes 0. So this terminates. Okay. I'll go to an example. Find the nth derivative of x cube into e power of ax. So this is the algebraic function here. First derivative 3x square, next 6x, and then 6, and then becomes 0. That means after 4 terms, this terminates. So I will take this as u and this as v, right? Then y equal to x cube into e raised to ax. Nth derivative yn equal to, and we know the nth derivative of e raised to ax as a power of n into e power of ax. Okay. The first term is x cube. N is 0 is 1. Therefore, I will write u as it is here. X cube into nth derivative of this. A power of n into e power of ax. Okay. And next, second term. Second term is NC1. Second term is NC1. Okay. NC1. NC1 is equal to n itself. NC1. Here I will write the derivative of this. Okay. X cube derivative is 3x square. And one less derivative of the second function. I have to write Vn minus 1. Replacing n by n minus 1, here I am getting a n minus 1 e power of ax plus. Next write nc2. Just write the derivative of this 3x square derivative 6x and one less derivative. Replace n by n minus 1 here. This becomes a power of n minus 2 e power of ax plus. nc3. Differentiate this 6x. I am getting 6 and one less derivative of this an minus 3 e power of x. And next, that this terminates here because next term I have to write the differentiation of 6. That becomes 0. Then remaining all the terms becomes 0. So that is e power of ax. Okay. Here e power of ax is there. I will take e power of x common factor. A raised to n, a raised to n minus 1, a raised to n minus 2, a raised to n minus 3. There I will take a to the power of n minus 3 common factor. Then in the first term I am getting x cube into a cube remains plus nc1. Here 3x square remains and a square remains plus here nc2. 6x remains. 1a remains plus nc3 6 remains, a raised to n minus 3 and e power of x is a common factor. So this is our nth derivative. Okay. Next example. If y equal to sin inverse x square, show that 1 minus x square into yn plus 2 minus 2n plus 1 into x into yn plus 1 minus n square yn is equal to 0. I have to show this equation. Okay. So let me consider y equal to sin inverse x whole square. First differentiate this equation 2 times and then differentiate n times using Leibnitz rule. Then we get yn plus 2. So differentiating this with respect to x, I am getting y1. Y derivative is y1 equal to sin inverse x whole square derivative is 2 into sin inverse x into sin inverse x derivative is 1 by root of 1 minus x square. Okay. And if I take the cross multiplication, I am getting root of 1 minus x square into y1 is equal to 2 into sin inverse x. Again differentiating this with equation with respect to x. On the left hand side, I have to use the product rule. First function derivative of second plus second function derivative of first. So that is root of 1 minus x square into y1 derivative is y2 plus second function is y1. Derivative of this root of 1 minus x square is 1 by 2 root of 1 minus x square into 1 minus x square derivative is minus 2x. Here I can cancel 2 and 2. This is equal to 2 into right hand side. Sin inverse x derivative is 1 by root of 1 minus x square. Now if I multiply this equation throughout by root of 1 minus x square, this becomes 1 minus x square. 1 minus x square into y2. Here 2 gets cancelled, minus root of 1 minus x square gets cancelled, x y1 remains, is equal to, on the right hand side 2 remains. So I am getting this equation after differentiating twice the given equation. Now if I use Leibniz rule to differentiate this equation n times, that is differentiating this equation with respect to x n times, I will take 1 minus x square as first function, that is u, and this as v. Okay. So differentiating n times using Leibniz rule, first I will keep this as it is, 1 minus x square as it is. I have to write the nth derivative of this, y2. Nth derivative of y2 is yn plus 2 plus nc1 is n into, I have to write the derivative of this. Derivative of this is minus 2x into 1 less derivative of this is yn plus 1 plus nc2. nc2 is nothing but n into n minus 1 by 2 factorial. 2 factorial is same as 2 into, I have to write the derivative of this, minus 2x derivative is minus 2 into 1 less derivative of the second, yn. Okay, so and next term becomes 0 because I have to write the derivative of minus 2, that becomes 0, or the next terms are all equal to zeros. So this is the nth derivative of the first term, 1 minus x square into y2. Next minus, here also I have to apply the Leibniz theorem. Okay, minus, I will take x as the first function, x into nth derivative of y1 is yn plus 1 plus nc1 is n into derivative of x is 1 into 1 less derivative is yn. Next term I have to write the differentiation of 1, that becomes 0. So this is the last term here, equal to, on the right hand side 2 is there, it is a constant quantity, its derivative is 0. Now writing the terms in order, 1 minus x square into yn plus 2, only one term is there. Next, yn plus 1 terms. See, this is 1 yn plus 1, here also we have yn plus 1, here x is there, here also x is there, and negative sign is there, negative sign is there. So I will take minus x into yn plus 1 common factor. What remains here is, here 2 into n remains, 2n, here plus 1 remains, because I have taken negative sign common factor, 2n plus 1 into x into yn plus 1, that is x into 2n plus 1 into yn plus 1 plus yn terms. This is 1 yn term and this 1 yn term. Here 2 gets cancelled. What remains here is minus of n square minus n. That is minus n square plus n. And here we have minus of n minus n. Minus n square plus n minus n. Plus n minus n gets cancelled. I am getting 1 minus x square into yn plus 2 minus of 2n plus 1 into x into yn plus 1 minus n square into yn is equal to 0. So this is the required equation. Okay. Next, one more example. If y equal to log of x plus root of 1 plus x square whole square. Okay, this power is for this whole. Show that 1 plus x square into yn plus 2 plus 2n plus 1 into x into yn plus 1 plus n square into yn is equal to 0. So given y equal to log of x plus root of 1 plus x square whole square. Differentiating this with respect to x once, we get y1 equal to, first power derivative, 2 into log of x plus root of 1 plus x square into log derivative, log of x plus this derivative is 1 by x plus root of 1 plus x square into this function derivative. X derivative is 1 plus root of 1 plus x square derivative is 1 by 2 root of 1 plus x square into 1 plus x square derivative is 2x. So this is equal to 2 into log of x plus root of 1 plus x square into 1 by x plus root of 1 plus x square as it is. In this term, 2 gets cancelled. I will take root of 1 plus x square LCM. This becomes root of 1 plus x square plus this x, that is x plus root of 1 plus x square. Now this x plus root of 1 plus x square, this x plus root of 1 plus x square gets cancelled. What I am getting is y1 is equal to 2 into log of x plus root of 1 plus x square into 1 by 1 plus x square remains, because these two terms gets cancelled. Now multiplying throughout by root of 1 plus x square, I am getting y1 into root of 1 plus x square is equal to 2 into log of x plus root of 1 plus x square. If I square this equation, I am getting y1 square into 1 plus x square equal to 2 square is 4 into, if I square this log of x plus root of 1 plus x square whole square is nothing but our y. Okay, this becomes 4y. Now differentiating this again with respect to x, what I am getting? Left hand side, here I have to use the product rule. First function is y1 square into derivative of 1 plus x square is 2x plus. Second function is 1 plus x square into derivative of y1 square is 2y1 into y1 derivative is y2. Okay, this is the left hand side derivative equal to, on the right hand side 4 constant as it is, derivative of y is y1. Now dividing this equation throughout by 2y1, 2y1 is common factor here. Okay, so dividing this equation throughout by 2y1, what I am getting here is 2 gets cancelled, y1 gets cancelled, I am getting xy1 here, plus here 1 plus x square into y2 equal to, on the right hand side I am getting 2. Now differentiating this equation n times using Leibnitz theorem. So this is xy1 plus 1 plus x square y2 equal to 2. Using Leibniz theorem here, I will take x as the first function u, x as it is, nth derivative of y1 is yn plus 1 plus nc1 is n into derivative of x is 1 into 1 less derivative is yn. Okay, next term becomes 0 plus, coming to this term here, 1 plus x square into nth derivative of y2 is yn plus 2 plus nc1 is n, derivative of 1 plus x square is 2x into 1 less derivative is yn plus 1 plus nc2 n into n minus 1 by 2 factorial into differentiation of 2x is 2 into 1 less derivative is yn equal to, right hand side is 2, derivative of 2 is 0. Okay. Now writing the terms in order, first I will write yn plus 2 terms here. 1 plus x square into yn plus 2, only one term is there, plus. Then I will write yn plus 1 terms. This is yn plus 1, here also I have yn plus 1. X is common factor here. So if I take x into yn plus 1 common factor, I am getting n here 2n plus here 1, that is 2n plus 1 into x into yn plus 1 plus. Then we write yn terms. Yn terms are 1 yn term is here. Here I can cancel this 2 and 2. Here I am getting n square minus n. Taking common factor yn as common factor, I am getting n square minus n plus n. Okay. So n minus n plus n gets cancelled. I am getting n square into yn is equal to 0. So this is the required equation. 1 plus x square into yn plus 2, 2n plus 1 into x into yn plus 1 plus n square into yn is equal to 0. Okay, this is the required equation. This is the required equation. Okay, we'll stop here.